For the student or the armchair scientist, bringing you everything scientific from the mundane to the seemingly magical. I'm AJ Thomas with Thomas Chemicals, and this is Latent Learned. Let's talk about chemistry, shall we? What is it? Where did it come from? Where is it going? And maybe the most important question, why should we care? To start with, let's put a definition to the term. It's a funny thing in that everyone thinks they understand what chemistry is until they really stop to think about it. So let's start with a thought experiment. Just for a second, I want you to think of a definition of chemistry. Scribble it down or repeat it to yourself. Whatever works for you. Got it? Now, there's two parts of the definition of chemistry. The first part probably matches what you thought of. It's the study of chemicals, or what we call substances. We'll come back to how we define chemicals in a minute. How are you doing so far? Pretty good? The second part is the study of how those substances change. Specifically, it's the study of chemical changes, or how one substance changes to another. Did you have that part? Don't feel bad if you didn't. It's something that most people don't think about. Most people think of chemistry in the same way of other sciences, simply as the study of some specific thing defined in the name. Biology, after all, is the study of living things. Astronomy is the study of space. But I digress. There's two parts to this definition, so let's talk about them individually. The first part is the study of chemicals, also known as substances, and we define chemicals as pure substances. They're made of one thing only, such as water or sodium chloride. These pure substances can then be classified as elements or compounds. Elements are the purest substances, and they can all be found on the periodic table. There are currently 118 elements known to be in existence. Compounds are two or more elements bound together by a chemical bond. There's several different kinds of bonds, but we'll talk about that another day. The important part here is that the elements in a compound cannot be separated without changing the substance. A really good example is sodium chloride. It's a white crystalline solid, also known as table salt. If you separate sodium chloride into its elements, you get sodium, which is a soft silvery metal, and chlorine, which is a noxious yellow-green gas. In this case, it's pretty obvious that sodium chloride is a pure chemical and very different from its components. So chemistry is the study of these pure substances, elements, and compounds. The second part of the definition refers to the changes that those substances can undergo. Specifically, as I mentioned earlier, we are talking about what's called chemical changes. See, there's two kinds of changes that we can define in science: chemical changes or physical changes. Physical changes are easier. They describe changes in what's called physical properties, or how something looks or feels. The biggest requirement of a physical change is that it cannot change the substance. Cutting and tearing are both physical changes, as are changes in physical state, such as boiling or freezing. In a lot of these changes, the substance itself doesn't change. Tearing a piece of paper results in two pieces of paper. It's still paper with all the same properties of paper, just smaller. Boiling water produces steam, which is just hot water vapor. It's still water. The key to a lot of physical changes is that they are, for the most part, reversible. Steam can be condensed back into liquid water. Torn paper can actually be turned back into a larger piece of usable paper with some work. If If, on the other hand, you burn the paper, it would never be changed back into paper. That would be a chemical change, also known as a chemical reaction, a change in which the substance is no longer the same. Chemical changes can be a bit trickier to identify because they involve changes on a molecular level. It's hard to imagine, for most people, the moving around of atoms and electrons, which is where reversibility usually makes things easier. The large majority of chemical changes are not easily reversible. Rust or corrosion is another good example of a chemical change, which again is irreversible for all intents and purposes. The rust on an iron bar will probably never again look like shiny metal like it once did. Some more subtle examples include cooking or metabolic processes. Once you've baked a cake, you cannot turn it back into raw eggs, flour, milk, and sugar. That's basically it. Chemistry is the study of chemicals, also known as pure substances, and how they change into other substances. But what does that look like exactly? I mean, yeah, we can talk about burning paper and weird elements all day long, but what does chemistry look like? How do you look at something and say, that's chemistry? And that is the awesome part. Chemistry can be found in every field and every discipline. It can be found in every part of our daily lives. There's chemistry in the soil and the air. There's chemistry in developing new materials and new technologies, and there's chemistry in every biological and ecological process known to humankind. To better describe what chemistry looks like, I'd actually like to talk about the 5 main branches of chemistry: organic, biological or biochemistry, inorganic, physical chemistry, and analytical chemistry. Organic chemistry and biochemistry are often confused with each other because we think of the word organic meaning natural things or living things. Organic chemistry is actually the study of carbon-based compounds, including but not limited to compounds which occur in living systems. Any compound that is majorly carbon falls into the purview of organic chemistry. That said, the majority of organic chemistry focuses on carbon, hydrogen, nitrogen, oxygen, sulfur, phosphorus, and halogens such as chlorine and fluorine. Carbon has its own field because it does a lot of things that other elements don't. These properties are believed to be why life on Earth evolved to be carbon-based or made of primarily carbon. Carbon can make very long and stable chains, which is a fairly unique property and allows for such large biomolecules as proteins and DNA. The formation of long chains of atoms is called catenation, and this is the reason why carbon is so prevalent in biological compounds. For example, in order to store all of the possible information needed for a complex organism, such as human beings, DNA must be fairly large. If carbon was unable to form long, stable chains, DNA would be restricted to a much smaller size. Other main group elements can also form these chains, also known as catenae, including sulfur and silicon, although they are more limited in the length of stable molecules that they form. In fact, the catenation abilities of sulfur and silicon is why science fiction so often imagines extraterrestrial life as sulfur-based or silicon-based. But I digress. Other properties of carbon related to these chains is the ability to form stable rings and higher order bonds, such as double bonds and triple bonds. However, with all of this variety, carbon is limited in its geometric orientation, which produces predictable three-dimensional structures, even for these very, very large molecules. In recent years, carbon has also been found to have some incredible electrical properties, as well as the ability to form truly amazing structures such as nanosheets and nanotubes, and has been found to be integral in the function of solar panels, I could go all day about carbon, but we'll leave that for another time. Biological chemistry, usually referred to as biochemistry, is specifically the study of chemicals and processes within living systems. Everything that a living organism does involves a series of chemical reactions. If I move my arm, there's a series of reactions going from my brain to my arm, telling it to move. There's another series of reactions that causes my muscles to contract in such a way that my arm moves just how my brain wants it to. There's a series of reactions that tells my lungs to open, bringing in air, and then transporting oxygen from my lung to every cell in my body. Even within the brain, there are reactions that allow the different parts of the brain to communicate with each other. If you think of any process within any living organism, from cell replication to eating to death, it can be reduced to a series of chemical reactions. These biological systems produce some of the most efficient processes, including some which have yet to be replicated outside of the living organism. These processes are so complex that a lot of them are not fully understood, but they have allowed us to take some substantial strides in alternative energy, crop production, waste management, medicine, and other fields. Inorganic chemistry is primarily a study of metals and metal-containing compounds. There's a lot of fascinating study in inorganic chemistry, including catalysis, colorant and protectant chemistry, medicines, fuels, materials, and nanotechnology. The microchips inside your computer are built with inorganic chemistry, as are the compounds within a battery. The technology that allows for the continuous miniaturization of computer parts is one that's of particular interest to me. Specifically, the ability to form nanoscopic machines and what I would call designer molecules. For example, we can now think of a shape which we want to build, such as a cube or a ring with a rod that goes through the center of it. And with a little study, we can build it out of atoms and molecules. The ring rod system specifically can then be used to form minuscule machines. This research may one day lead to microscopic computer chips. Physical chemistry is best described as the point where physics and chemistry collide, or as I like to put it, the study of the physics of chemistry. Physics could be considered primarily as the study of where things are and how they move. Thus, physical chemistry focuses on the study of where things are within molecules and between them and how they move. The latter part includes how the atoms move within the molecules, including the strength and flexibility of chemical bonds, how molecules and atoms move relative to each other, and how atoms and electrons move during chemical reaction. This fascinating field covers molecular structure, reaction rates or the speed of a reaction, some molecular physics, and quantum mechanics. It's actually my personal official area of expertise, specifically in the area of microwave spectroscopy, which involves the determination of molecular structure and motion in gases. Where physical chemistry is the physics of chemistry, I like to think of analytical chemistry as the math of chemistry. Formally, it's the science of determining what substance is there and how much. It seems perhaps like a trivial thing, but it's arguably the most prolific and popular branch of chemistry, not to mention vitally important. Analytical chemistry overlaps with all the other branches and includes practical applications such as the determination of the safety and quality of food, drugs, and water, disease diagnosis, and the development of legal and technical procedures with regard to those analyses. The process that determines if there's lead in water supplies and what levels are considered safe or unsafe is analytical chemistry. The person who makes sure that the correct elements in the right ratios are in the steel in your car is probably an analytical chemist. the blood tests used by doctors to diagnose diseases from anemia to multiple sclerosis all involve analytical chemistry. It's easy to think of it as an underlying current that flows through all branches of chemistry rather than a separate discipline, but it should be recognized as a distinct field with its own specialties. All of these branches, while they have their own focuses, actually overlap more than you might think. Of course, analytical chemistry can be found very easily in every other branch. If you're making a compound, you have to be able to determine that it's there and how much you made. Otherwise, how do you know it worked? There is actually such a thing as biophysical chemistry, which might study the rates of biochemical reactions or the structures of biochemicals themselves. Of particular interest in structural studies are very large biomolecules, such as DNA, protein, and even seemingly ordinary things like spider silk. Organometallic chemistry researches carbon-based metallic compounds, making it the seemingly unusual overlap between organic and inorganic chemistry. There are a lot of other fields and subfields of chemistry which I won't get into today, such as polymer chemistry, environmental chemistry, medicinal chemistry, theoretical chemistry, thermochemistry, and electrochemistry. Suffice to say that chemistry is involved in every aspect of the world, in every job, and every field of study. In fact, it has been a long-standing challenge I have given to my students to name for me a career or job which doesn't involve chemistry. I have yet to be presented with one which I cannot make that connection. Now that we know what chemistry is, where did it come from? It's not like Neanderthals started building beakers after they made the wheel. Even though that seems like a far-fetched example, it says that the history of chemistry is the history of civilization. Since early hominids started building fires, cooking food, and tanning leather, we have been using chemistry. It's a discipline that has evolved with mankind and in many ways allowed for the evolution of mankind. But that's not what most people mean when they ask for a history of chemistry. Most people are asking for the history of what we now recognize as the study of modern chemistry, and that typically begins in ancient Greece. Now, this early history is highly debated, as most early cultures had some form of what's known as natural philosophy and some understanding of chemistry. Natural philosophy is, put simply, philosophical speculation about observations in nature, or trying to find a logical explanation for natural events in the world. Ancient Egyptians had an understanding that the iron formed from falling stars, or as we would now call them, meteorites, was not the same as the iron they pulled from the ground. In fact, Egyptian metallurgy and mineral work was largely unmatched by the rest of the world for centuries. The Far Eastern civilizations were known for their studies of chemicals, producing effective medicines and marvels such as gunpowder, as well as their own feats of metallurgy. The first element to be formally discovered was copper in 6000 BC in Anatolia, a peninsula in what is now known as Western Asia and the Middle East. Most early civilizations around the world utilized some level of chemistry, developing medicine, tools, and other essentials, but there was a lot of emphasis on metals and medicine, as they were very integral to the success of a people or a civilization. I will come back to those patterns and their significance later. Unfortunately, the study of chemical history tends to be Eurocentric, in part due to the detailed and readily translated records of Grecian natural philosophy. And so this is where we will begin our story. Most mark the beginning of chemistry with the philosopher Democritus, who is among the first to theorize that there was a smallest piece of material, and he dubbed it atom. The word atom comes from the Greek word atomos, which roughly translates to cannot be cut. The idea was that if you took a grain of sand and you cut it in half, and half again and again and again, eventually you would reach a point where you cannot cut it anymore and still have sand. The smallest indivisible particle was imagined as an atom, a term which has persisted through history, although what an atom is believed to look like has certainly changed. These theories included the shape and texture of the elements, as well as mechanical connections between the particles based on their macroscopic properties. These atomists, as they were called, believed that water atoms were smooth and slippery. Iron atoms were solid and strong, with hooks that connected them into large pieces. Another well-known philosopher of the time, Aristotle, postulated that there were 5 elements: earth, water, fire, air, and ether, the last being his own addition to the theories before him. He and others like him believed that these elements combined in differing proportions to make up everything in the observable universe. For example, earth and water might combine to form plants, but the difference between the more solid woody plants and flexible grasses lies in the ratio between them. Ether was the circular medium which carried all heavenly bodies in their orbits. All of this development in natural philosophy occurred around 400 to 300 BCE, or nearly 2,500 years ago. The next big leap in chemistry came with the development of alchemy. Remember how I said there was a trend that early civilizations frequently had extensive work in metallurgy? Thanks to Aristotle and the insatiable greed of humanity, the field of alchemy grew steadily from about 300 BCE to 300 AD. For over 600 years, there was an entire movement, a subsection of metallurgy, really, devoted to the singular goal of transmuting lead and other cheap metals into gold. Gold was chosen due to its beauty, malleability, and corrosion resistance, in addition to its rarity. Many cultures believed gold was a symbol of not only wealth, but immortality. The word chemistry is actually believed to come from the word alchemy, which takes its origin from the Arabic word al-Khamia. That term may have ultimately began from Kemet, the name for Egypt, or the Greek word chemia, meaning cast together. Now here's the fascinating part. The study of alchemy essentially founded what we know as modern science, where previously theories were largely untested and what tests were performed were not commonly recorded. Chemists began running extensive tests and recording each step and result. Why? Because if they were successful, they would need to be able to repeat their experiment. Alchemy pushed a greater understanding of metals and their properties, as well as a boom in technology following the hope that transmutation could be mechanized. This fascination with creating gold, as well as the parallel obsession with chemical immortality, lasted from approximately 300 BCE to the end of the 1600s, nearly 2 millennia. Why is this significant? For one, the field of alchemy was specific to the Mediterranean regions of Europe. Areas like the Central and Southern Americas and Africa had generous quantities of gold, and we see this reflected in the artifacts of the time. But gold is heavy and difficult to transport, especially over long distances. The sunken Spanish galleons with coffers full of gold have become a historical and mythological testament to that fact. If gold had been plentiful or held in lesser regard, or if the other ingredients used in alchemy had been scarce, this enormous revolution of science may never have happened. It's a fascinating thing to think about, isn't it? But getting back to our timeline, the end of alchemy in the late 17th century ushered in an era of what is referred to as traditional chemistry. From the early 1700s to the early portion of the 1800s, chemistry was defined by a greater understanding of particles and elements. Antoine Lavoisier showed that oxygen was required in combustion reactions, or reactions which produce fire, formally naming the element in 1771. In fact, 33 elements were formally discovered and named in the time between 1700 and 1808. Charles Coulomb, the discoverer of Coulomb's law, determined that the force between two particles is proportional to the distance. While a simple sounding theorem, it allowed for a greater understanding of electromagnetic properties, which gave rise to some fascinating research in the next era of chemistry. John Dalton developed his atomic theory during this time period as well, a series of rules which govern the behavior of atoms. It is this event which is commonly used to distinguish between traditional and modern chemistry, where the focus turned to analyzing atoms and what lies within them, in addition to reactions on a larger scale. Shortly after Dalton's atomic theory was penned, in an era known as that of modern chemistry, a Russian researcher developed the first modern periodic table. His name was Dmitry Mendeleev, and as the story goes, he woke up one day in 1869 with an idea, which came to him in a dream. This epiphany was to arrange the elements not by mass, as previous attempts had done, but by their chemical and physical properties. Not only was he able to align these elements into a working table, but he found gaps and in the process correctly predicted the properties of elements not yet discovered. This early table has now been expanded and rotated to form the current periodic table of elements. We now know that not only were these elements arranged by their properties, but by the number of protons in each element. During the same time period, the advent of vacuum tubes, and with that, cathode ray tubes, ushered in a new level of understanding of what lies within an atom. Up until this point in time, atoms were still considered theoretical. They wouldn't be definitively proven to exist until the early 20th century. In 1879, William Crookes used the vacuum tube invented over 20 years earlier by Heinrich Geissler and added a zinc sulfide coating on one end, a cathode on the other end, and an anode in the middle. An electrical current was applied between the electrodes, which caused the zinc sulfide to glow. Crookes believed that rays from the cathode caused the zinc sulfide to glow and called his device a cathode tube. This new invention became a vital tool in research until the end of the century. It was used by Goldstein in 1885 to discover the proton by filling the tube with hydrogen and separating the electrons. He was able to measure both the charge and the mass of this novel particle through this experiment. In a similar experiment in 1897, Thomson placed the tube into a magnetic field and determined the charge and the existence of another subatomic particle, the electron. This experiment won him the Nobel Prize in Physics in 1906. Röntgen, while researching the light produced from cathode ray tubes in 1895, discovered that the rays caused from fluorescence could pass through even walls. These rays are now used as an important medical diagnostic tool. We call them X-rays. The cathode ray experiments continued and by extension gave rise to a new field of study, radioactivity and radioactive elements. It was during this time that the Curies performed their groundbreaking research, discovering radium and polonium, as well as many of the effects of radiation. This last field gave birth to the discovery of additional types of radiation, fission reactions, and culminated with the Manhattan Project in the 1940s. When people discuss modern chemistry in history, they tend to stop there, as though the culmination of modern chemistry ended with the development of nuclear energy and weapons. However, I'd like to highlight some of the more recent and highly important developments in chemistry to demonstrate the continuing impact being made in the field. Synthesis of chemicals has taken huge strides in the last 100 years, resulting in, as I mentioned before, the possibility of designer chemicals, or substances with structures made to order. Thanks to these improved processes, chemists can now synthesize compounds previously only found in nature, particularly medicines, thus reducing the need to harvest them and deplete those natural resources. Even for compounds that could be synthesized before, better methods that use or produce less toxic byproducts and work at a higher efficiency have been developed for lab and industrial use. The development of synthetic polymers has been enormous in the last century. To illustrate this, just look around you and try to find one item that's not made of or covered in plastic. Plastics were put into common use arguably only in the last century or so. With the development of computer technology in the mid to late 1900s, it seems like everything we touch has plastic in it or on it. But plastic is not the most fascinating new material of this era, not by a long shot. We now have optical materials that can deliver information at near light speeds with very little signal degradation. There is interest in magnetic nanostructures that could miniaturize magnetic media to unprecedented levels. Imagine if each memory bit in your computer took up only the space of a single molecule. Carbon, as I mentioned before, has found new structure in the past few decades. Fullerene and nanotubes, which bear pentagonal and hexagonal shaped carbon structures, are electrically conducting despite the insulative nature of carbon and are incredibly strong for their size. Graphene, which has a similar structure to nanotubes but in a sheet, was characterized only a few years ago in 2004. It is a layer of carbon just one atom thick, but it is incredibly strong, waterproof, flexible, and an effective superconductor. It is considered the strongest material on the planet, 200 times stronger than steel, and transparent. Our understanding of the environment has also evolved, with chemists around the world becoming painfully aware of the long-term effect that the products and byproducts of reactions has on the world around us. The replacement of CFCs and toxic solvents in industries with safer alternatives has already shown positive results. The development of new and better energy sources has eased the dependence of the world on our depleting fossil fuels as well. The scientific community has begun to fully realize something that hadn't really been thought of before the mid to late 1900s. What we do now will affect the world and the future. Whether the effect is a good one or a bad one is up to us. And that's the note I want to end on. What you do now, no matter what you do, is going to affect the world in ways you may not even imagine. It is up to you if the effect is a positive one or not. Knowing what chemistry is, being able to define it and recognize it, is just one piece of the puzzle as a scientist. The real question here is, how do we use chemistry and the other tools we have to shape our world for the better? Thank you so much for joining me today. I hope that you have learned something about chemistry, if only the ability to more sincerely appreciate it. Chemistry is truly a fascinating science with roots that extend through history, even to prehistoric times. I look forward to sharing more about the amazing world of science with you. Until next time.